The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hello and welcome. So, like last time, the important announcement is, of course, that we have an exam coming up. So exam 2, Wednesday. Everything's very similar, analogous to last time, with the exception that we're in Walker. Don't go to building 26, go to Walker. Other than that, things look very similar to before. The idea will be that the exam will focus on things since exam 1. However, this subject builds on itself. So the official coverage is 1 to 12, lectures 1 to 12, recitations 1 to 12, and homeworks 1 to 7. Questions, comments? All the logistical issues are clear? Yeah. So there was an introduction to root locus. So everybody knows what root locus is? So you can find out after class. It'll just make me feel a lot better if you nod your head yes. Okay, so root locus is the way you figure out the locus of possible points that a pole could move to. There's an enormous number of rules for thinking about how root locuses evolve. And if you're a really good signals and systems person, you know 50 rules. That's not the point of this class. You should know that poles move around when there's feedback. We'll have examples of that in class today. You should be able to calculate how they move around for simple problems. You're not expected to know the rules. Okay, so you shouldn't be surprised by the rules. If we ask you to derive one of the rules, you probably could, but we don't expect that you've memorized the rules. Does that sound roughly correct? Okay, question. Other questions or comments? Content, administration, anything like that? Okay, so about a week ago, Russ introduced the idea of using feedback for the purpose of controlling, and the example in lecture was controlling a robot. You've seen that before, right? That's 601. And then in recitation yesterday, he went over some more ways of thinking about more sophisticated ways to do control with feedback. And the point of those more sophisticated ways to do control is really performance. The idea is to enhance performance. And that's the theme that I want to build on today and on Tuesday. How do you enhance performance by using feedback? And we'll go through a number of examples. You can use feedback to increase speed and bandwidth. You can use feedback to change the control variable from, I'll do an example, speed to position. You can reduce distortion, reduce sensitivity to parameter variation. You can stabilize unstable systems. We'll do a bunch of examples. The point is that you can use feedback to accomplish a lot of different tasks that, generally speaking, improve performance. So with that, let me think about an op-amp. You all know about op-amps, right? That's also a 601 sort of thing. So an ideal op-amp would have a bunch of properties that we would like. We'd like it to be very high speed. We'd like it to have a very broad bandwidth. We'd like it to be fast. We'd like it to have a very low output impedance so it works like a perfect voltage source. We'd like it to have a very high input impedance so that when we hook it up to something, it doesn't change to something that we hooked it up to. There's lots of things we'd like it to have. Unfortunately, it's difficult to build a circuit that has all of those things. And so here's an example of that. Here's one of the world's most popular op-amps, the LM741, invented eons ago and still used today. The idea that's plotted here is the frequency response. You remember frequency response. What's the frequency response of an LM741? Well, if you plot as a function of frequency how does the gain change? Well, the gain's enormous. High gain, that's what we'd like it to have. The gain's enormous at low frequencies, at 1 radian per second. But the gain becomes very small out at high speeds, at the speeds that we think about when we're thinking about communication systems or when we're thinking about computation or things like that. When we think about speeds that are electronic speeds, the gain is actually pretty small. Similarly, the phase changes. The phase at very low frequencies is near 0. That's kind of ideal. 0 would mean in phase. The output reliably tells you what's the input doing. So that's good. But as you go to higher frequencies, you start to pick up a phase delay, which means the output's telling you what the input did a little while ago. OK, that's less good. So the performance in terms of providing a lot of gain is quite good for some frequencies, but not for others. Unfortunately, the range where it's not very good is most of the range. So if you thought about an op-amp doing even a very low frequency problem like audio signal processing, most of the frequencies that are of interest to audio are in the region where the op-amp's not working too well. We hear sounds from about 20 hertz to about 20 kilohertz, and that range is indicated by the red arrow, and you can see that's not where the op-amp is working ideally. Similarly, we would like the op-amp to be fast. Fast is indicated here by thinking about the step response. So if you thought about having an ideal step at the input, what would the output look like? Well, we'd like it to be an ideal step, but it generally isn't. Generally, there's some lag that's associated with that phase delay that I talked about. And in fact, what I'd like you to do is figure out exactly how it's associated with that phase delay. Figure out, it will turn out that the step response can be characterized by a time constant tau. The time constant tau is the time required for the signal to get within 1 over e of its final value. Determined from this, I've already told you the performance parameters in terms of frequency. You should be able to use 6003 to figure out what that implies about time. So look at your neighbor. OK, look, right, look. And now figure out which answer, what's tau for the 741 op-amp. OK, it's dead quiet, so I assume that means convergence. So what's the answer? What's the time constant tau of the 741? Raise your hand with a number between 1 and 5. Don't look at other people, just raise your hand. OK, I see a couple answers I don't like. How do I think about converting this representation to that representation? What should I do first? Shout. I start with the thing on the right. What should I do next? So we're looking for something like e to the minus t over tau. That's right. We're looking for something like that. How do I get that starting with the thing on the right? Poles, what a good idea. How do I figure out poles from the thing on the right? 6003 poles, that should be like a hard wire, right? So when you hear the word 003, you should think the word pole. How do you associate a pole? Can somebody tell me what the poles of the right-hand system should look like? Where the line is. There's a couple lines there. The vertical line. How many poles are on the right? How many poles are in the system represented by the right-hand figure? One. How many zeros? Zero. Wonderful. So we have to think about a pole, just one pole. So we think about the S-plane, right? Where's the pole? Oh, you already told me. 40. OK, where's 40 over here? Somewhere in there. Got it. Where's the pole over here? It's at location 40. That's actually correct. Well, sort of. Negative 40, that's exactly correct. So negative 40, so the pole is right here. OK? So the pole's at minus 40 radians per second. How do you know that? Well, that's that Bode stuff we talked about last time, right? So if the pole were here, you would think about a vector. So this is the j omega axis, right? You would think about a vector connecting the pole to some location on the j omega axis. If the location is omega small, it's going to have that vector is going to have some length like that. It's going to have an angle of 0. And as frequency goes up, the vector gets longer, which means that the magnitude gets smaller because the pole's in the bottom, right? And the phase goes increasingly toward pi over 2, but it's in the bottom, so it's minus pi over 2, right? So the frequency at which you get to pi over 4, okay, pi over 0, pi over 2, the frequency at which you get to pi over 4 is, so pi over 4 is here, right? So the distance here, the critical frequency, the frequency at which the phase is pi over 4, minus pi over 4, is going to be the same as the frequency of the pole. So that's how we know it's at minus 40, right? So we know that this then is a characterization of that system. It's not quite done. So what's the h of s for this system? If I've got a pole at minus 40, what's h of s look like? Shout, shout. Exam 2 is coming up. This is perfect practice.
I don't talk too much.
What's h of s look like?
It says something over s plus 40.
Exactly. Something over s plus 40. What would you like the something to be? We'd like it to be some k. We'd actually like it to be related, for example, to the open loop gain. So how big is the gain? How big is the gain when frequencies go towards 0? What's the gain at 0? Let's say the gain of 0. Let's define the gain of 0, k0. Let's define the gain at 0 to be, so what is the gain at 0? Ten to the 5. 2 times 10 to the 5. Right, it's a little bit above the 10 to the 5 line. OK? So now if I define k naught to be that gain at 0, what's the numerator over here? If the numerator over here were 1, what would be the low frequency gain? 1 over 40, right? To think about frequency, we think about 1 over j omega plus 40, right? You substitute s equals j omega to think about frequency. And if omega is very small, you get 1 over 40, right? So if you wanted that to be 1, you'd have to make it 40. But we don't want it to be 1. We want it to be k naught, so you'd want it to be 40 k naught. Or to be a little bit more general, we'd like this to be of the form alpha k naught divided by s plus alpha, right? So now we've got the Laplace transform. We can figure out the time response. What's the time response associated with that Laplace transform? You remember the impulse response of a system is related to the system function via the Laplace transform, right? So all we need to do is take the inverse Laplace transform of that thing, and we get h of t. So what's h of t? Okay, it's such a strain. All those weeks ago. E to the minus t, e to the minus something t. So we need something like e to the minus what? Alpha. E to the minus alpha t u of t. And there's going to be that thing's going to come out here too, right? It's going to be like that, right? And then if you wanted to find the step response, what would you do? H of t is the impulse response. How would you find the step response? A step is related to the impulse by integrating. The step response is related to the impulse response by surprisingly integrating. So you would integrate that thing, and you would end up with something, right? So you would get something like k naught 1 minus e to the minus alpha t u of t, something like that. I think that's right. Okay? The time constant is given by alpha, right? So what is the time constant now? 1 over 4d, right? So it's alpha t, but the time constant is t over tau. So the time constant is the inverse of frequency, right? Frequency is per second. Time constants is seconds. They're reciprocals of each other, okay? So the idea then is that we can associate a time response with that, and that time response is pretty slow, right? A 40th of a second, 40 things per second kind of. That's my speed, right? That's not computation speed, right? So that's pretty slow, and so we'd like to improve that, and one way that we can improve it is by thinking about feedback. So the idea would be we don't use the op-amp just out of the package the way it comes. We put it in a feedback loop. So for example, here you could put it into a non-inverting amplifier where you take the output, divide it by a voltage divider, and feed that back in. In 6003, the way we'll think about that is that the effect of this plus and minus input is to take the difference between two signals, right? We're going to take a circuit diagram and turn it into a integrator gain adder diagram, a block diagram. We're going to take a circuit and turn it into a block diagram. So the way we think about the plus and minus input of the op-amp is as a subtractor. And then this k of s that characterizes, so this thing, right, this thing here, we plug in there just as a box. And the effect of the resistors is to divide the output signal by some constant beta. So we can reduce the circuit to a 6003 equivalent, and then we can use Black's equation and all those other things that we do in 6003. So we can write an expression then for the closed loop system that looks like k of s over 1 plus beta k of s. Make sense? So then, as we've already seen, the op-amp by itself looks like a pole at minus 40. So we can substitute this expression into that expression for the closed loop, and we get a new closed loop. So h of s, which had been alpha k naught over s plus alpha, becomes, the new value is alpha k naught over s plus alpha plus alpha beta k naught. Okay, so the point is that we can think about the way the feedback changes the system function by just formulating what's the circuit look like in terms of a 6003 block diagram. Okay? So now, the effect of that, it looks as though what happens is the pole went from here to here. How big of a change is that? What's the biggest change in the position of the pole that you can achieve using feedback? No, I'm sorry? I want a factor by which you multiply alpha to find the biggest place that you could have put the new pole. I didn't say that right. I didn't say that right. I want to know where's the new pole. Sorry, I confused myself. Where is the new pole? How left can you put the new, how left can you get the new pole to be? What's the furthest, left is good, right? Left is good, everybody knows that, right? So right is bad. So small distances and the S-plane correspond to slow responses. Big distances correspond to fast responses. That's what we saw in part 1. So we're trying to push the pole that way as far as we can. How far can we get it to go? Okay, everybody raise your hands. The answer is, and again, I see lots of answers I don't quite like. With a minor perturbation, all those people who I don't like can become right by saying. So a lot of people have said this, which I don't quite like. What's the biggest distance that I can move it? Okay, new vote. I didn't like 2, and so therefore I will change my answer to 4. Wrong. No. How big can beta be? How big can beta be? What's the biggest possible value of beta? 1. So how far can I push it to the left? So I can push it this far, right? So if I make beta 1, that's as far as it goes. Beta 0 is kind of the rightmost position. Beta 1 is the leftmost position. I can get it that high. But that's very good, right? 1 plus k naught. K naught is a number like 10 to the 5th. So I can get it like 10 to the 5th bigger than it was. That's enormous. That means that I can stretch the frequency response. If the pole is the thing that determines the frequency response by that construction up there, I can stretch the frequency response by 10 to the 5th. That's huge. Pure win, right? Well, that doesn't sound right. So I've stretched the region where the gain is constant. I've stretched the region where the phase is close to 0. It's 100% win, except that I've cheated when I drew the plot because I normalized it by the DC gain. DC, I probably didn't define that yet. DC is direct current. It has nothing to do with current or direct. DC means 0 frequency. I have no idea why we insist on using that word, but we do. DC means 0 frequency. Okay? So you just do that automatic mapping in your head. Every time I say DC, I mean 0 frequency. Everybody else talks that way too. So the DC gain, I've divided the magnitude by the DC gain, h of j0. So this is the relative frequency magnitude, h of j omega, divided by the magnitude at omega equals 0. Had I not done that, the picture would have looked different. If you think about what happens, so the top curve here shows what happens when shows the response curve for a 741 op amp with no feedback. It has a pole at 40. It has a pole at minus 40, to be a little more correct. So there's a single pole at minus 40. That corresponds to beta at 0. That's open loop, no feedback. Okay? And what you can see is the DC gain is 2 times 10 to the 5th. And there's an AC gain defined by the cutoff frequency. If you compare this expression and that expression, the interesting thing that happens is that the DC response depends critically on beta, But the high frequency asymptote doesn't depend on beta at all. The high frequency asymptote of this is alpha k naught over s. The high frequency asymptote of this is alpha k naught over s. They're the same high frequency asymptote. What happened was that as I increased the feedback, I lopped off the low frequency gain, which had the effect of making the frequency look like it got very big. So pure win, no. Almost pure win, yes. Okay, I've traded, the trick is, I've traded gain for bandwidth. That's important because the folks who know how to microfabricate things know how to make things with very high gain. Making things that are fast is harder. This is a way that we can take advantage of the relative simplicity of making things with high gain to make them behave as though they're fast. Okay? You can see the same thing if you think about the response in time. If you think about the response in time, we're going to go from e to the minus alpha t to, I guess I didn't write it down. It's going to be e to the minus alpha 1 plus beta k naught t. Same factor. It's going to get 10 to the 5th times faster. Again, looks like pure win, but that's because I've cheated, because I'm plotting via this normalized final value that depends on beta. If beta were 0, the final value is 2 times 10 to the 5th. If beta is anything else, the final value is smaller. If I plot it not normalized, you get a kind of different picture. So if you were to use it, if you were to use the op-amp open loop, the response has a time constant of 1 over 40, as we said before. If you include feedback, it decreases the final value, but has the property that it does not change this slope. So if you think about this, this is an analytic expression for the closed loop step response, right? I get that by integrating one of these expressions. I didn't write the beta one down. I need the beta equivalent one of these. If you write the beta equivalent one of these, which is on a previous slide, and integrate it, you get this expression. And if you differentiate this expression with regard to time to find the slope at 0 is unchanged by beta. Because the exponent here, 1 plus beta k naught, has the same form as the denominator here. So when you differentiate it, this comes down, the two cancel, and you end up with a slope that's independent of beta. The effect of that is that if you change the final value, it appears to go much faster. So pure win, no. Apparent win, yes. We've traded gain for speed. Okay? So that's ways that we can use feedback to improve the performance of an op-amp. Okay? The big performance parameters that I talked about today were bandwidth and speed. You could do the same kind of analysis with many different kinds of metrics for op-amps, like output impedance, input impedance, distortion reduction. We'll do distortion next time. So there's lots of other things that feedback improves. I've illustrated it with 2. In both of those, as will be the case in all of the others, the effect of feedback is to trade gain for something else of interest. Okay, the next example I want to think about is thinking about a motor controller, where what I want to think about is changing the way we think about the input-output relationship. So I take a motor, that's my motor, and what I want to do is have it control position. So it's not too easy to see probably because it's such a tiny little motor. Actually, it's not a tiny little motor, it's an enormous motor. So the red bar, that's the shaft, right? And so the first question I want to think about is what's the relationship for the motor? What's the relationship for the motor for the transformation from voltage to angle of the shaft? So what's the relation between V of t and theta of t for DC motor? This is very much the same problem you worked in the head turning problem in 601. So you should be able to remember this answer from 601. What's the relationship between the voltage into a DC motor and the angle out? Is it 1, 2, 3, 4, or none of the above? Talk to your neighbor, figure out the right answer. So what's the answer? 1, 2, 3, 4, or none of the above? Everybody vote. You're on such a streak. More than half the answers I really don't like. Okay, so we'll do a demo and we'll figure out. So the question is, what is the relationship between voltage and speed? So I've got a motor and I've got a knob that controls the voltage that goes to the motor. Okay, so now I turn the motor on and nothing happens because I preset the voltage to be 0. Now I'll turn the voltage to the right to make the voltage a bit positive, more positive, back towards 0, at 0, negative, more negative. Okay, so what's the relationship between voltage and angle? So V is voltage, sorry. V is voltage, theta is angle. Angle, so here's 0, here's 90, here's, so here's 0, pi over 2, pi, right? The question is, what's the relationship between the voltage input to the motor and the angle of the shaft at the output? And now the answer is, okay, the number correct has not changed. So tell me in words, forget the 1, 2, 3, 4. What's the relationship between voltage and angle? What is proportional to voltage? Angular velocity is, so how do I get angular velocity?
The angle?
So I'm giving you the angle, theta of t. How do I get angular velocity? Take the derivative, yes. So what I want is that theta dot proportional to v. Okay? Which of those relationships say that? None of them. Okay? It was a trick question, of course. So what do I want to have as my model for the DC motor? I want my model to take a voltage in and give me theta out. What should be in the model? K. It's always good to throw a K in. That always works. Excellent answer. K always works, sure. In any physical system, you never get 1, right? Yeah. You're going to need an integrator, exactly right. So it's going to need something like, I think I called it gamma. A being the accumulator guy, right? A different way of saying that would be, write it in terms of Laplace transforms, I would get gamma over S. So if I put V in and I want to get theta out, right, I need to put it through an integrator. So the idea is that if I put a constant voltage in, say the voltage is 0, theta was flat. But if I put a voltage at the blue line, theta increased at some rate, and if I changed it to red, it increased faster, just like an integrator would do. So what I want to do is think about the motor being an integrator. Okay? That lets me then cast the motor, which is a physical thing, into 6003 terms again. So now I can think about the problem. I'd really like it not to be a speed controller. I'd really like it to be a position controller. So feedback to the rescue. What I'll do is I'll put it in a loop. So the idea is going to be that I take my motor, which looks like an integrator, gamma A, feed back a signal that's proportional to the angle, which I derive by having a potentiometer strapped to the back of the shaft. So there's a pot. I've taken off the little stop so that it spins around and doesn't hit the stop, right? Otherwise, it would be kind of bad for the first part of the demo. So it's a surgically altered potentiometer that spins around forever. But over most of the range, it's reporting angle. So that's the way I get this feedback loop in. And then I put it into this thing, which is really just a 741 wired up like I showed in the first example, so that it would take the difference between two things, the desired input, which is a potentiometer that I'm turning here, and the actual position, which is the potentiometer up here, the same kind of potentiometer, just one that I turn, the other the motor turns. And the op-amp figures out the difference, multiplies it by a gain alpha, and presents it to the motor. That's the idea. And if you just think about 003, it's pretty easy to see that you can represent this relationship by a single pole, right? There's some annoying constants, right? You have to worry about the gain of the amplifier, the gain of the motor, and how much feedback, that's alpha, beta, gamma. But pretty much it's just a pole. So what happens then as you change the gain? Well, if the gain is 0, the pole, so if the gain beta is 0, the pole is at 0. Okay, it works just like an integrator. That's what we said before. That's a sanity check, right? When you check something you already know the answer to, right? So if you set beta to 0, you get that the transformation is an integrator. Good. If you set beta and anything else, what happens? Well, the pole goes screaming out that way. That's good, right? Remember, good is that way, right? That's not always true, but when you're trying to make something work fast, that's the rule, right? Fast is over there. So the idea then would be that if I hook up this circuit, right, I take the feedback, run it into an op-amp, multiply, use that to control the motor instead of my turning the knob, then this thing should have the behavior that the pole goes from the origin to the right. So the question is, if that happened, what would happen? Okay, just doing the same kind of analysis that we did for the op-amp, the step response goes from being the response of a pole, which is an integrator, to being this kind of a response, which has a final value. That converts it from being voltage to velocity into voltage to angle. Does that make sense? It used to, when the feedback was 0, the pole was at 0, so the output continuously rose. There was no steady state position. But now with feedback, I get a step response that has a final value. The effect of moving the pole is the same as the effect of moving the pole in the op-amp example. I get a step response that becomes increasingly like a step. It goes from being a sluggish step to a fast step, okay? So that's the way I use 003 to use feedback to fix the motor, and I've done that. So I have to move the input to the amplifier from my pot to the op-amp, which is there, hopefully. So now when I turn it on, it becomes a position, okay? And I can test that by turning the pot. And in fact, when I turn the pot, the motor moves. Wonderful, voila, I won, right? Great, yes, yes, applause, please. Come on, come on, come on. Yeah, exactly, exactly. Okay, well, it's pretty wimpy, actually, because I've got this motor that weighs about, I don't know, 3 pounds, and it's exerting about a quarter of an ounce of torque. It's not really very impressive. So how do I fix it? What do I do? How do I fix it? I have a wimpy controller. Yes? More gain. More gain, of course. So remember that response. So now I turn off the motor and increase the gain by a factor of 3. And the answer is much better. Well, maybe. So what do? More gain, of course. So another factor of 3. Much better. Well, maybe. So another factor of 3. Okay, another factor of 3. Another factor of 3. Some of you close may hear that there's a little buzzing sound now. I can hear it. That's the op amp killing itself. Okay, it's not working. Why is it not? So is it working? I just gave it away. It's not working. How do I know it's not working? Here's my theory. Here's my answer. How do they match or mismatch? Is it an angle controller? Yes or no? Yes. Yeah, it's an angle controller. What's different about this behavior and that behavior? There's oscillation, right? This thing, turn it back on, let the thing kill itself. There's an oscillation. Turn the gain down so it doesn't kill itself quite as quickly. It's oscillating. Watch the oscillation, right? Think about characterizing the oscillation. Make the gain smaller. Well, that's bad. Ignore that. Think about the oscillation. It's still oscillating. Factor of 3 smaller. It's still oscillating. That doesn't oscillate. What's wrong? Okay, so the $64,000 question. What did I do wrong? Right? The goal was to make a model of the motor, analyze the model, figure out how to put feedback around it, make it perfect. Yes? I made too simple of a model for the motor. I ignored inertia. I ignored all manner of things. I ignored friction. So how can you tell that I ignored those things? So one way you can tell, let's see, so is it off or on? It's on. So turn it off. Go back to the original configuration where it's a speed controller. Turn the speed on a little bit. Turn it off. Grab it with my fingers. Turn it on. Now release it. What did you see? Grab it with my fingers, turn it on, let go. We're trying to poke a hole in this. There's my model. My model's wrong. I claim I just told you the key experiment for figuring out why my model is wrong. Now you have to figure out how to interpret that experiment. So what does my theory say would happen if I turn on the power, hold the bar, and release it? It should instantly reach the terminal velocity. What's it doing? It's ramping up. That's what's wrong with my model. Okay? So the model is too simple. It's not just an integrator, it's a slow integrator. Okay, I can model that too. If I model the slow integration, I can think about the motor doesn't really behave like an integrator. It works like a sluggish integrator. That might be a little easier to see if I write that in S. So that's the same as gamma P over S plus gamma, no, S times No, close, wrong. So it used to be gamma over S. Now it's gamma over S plus P. Okay, so I'm replacing what had been an integrator here with a sluggish integrator. Sluggish is another pole. So instead of representing it by a single pole at the origin, I represent it by two poles. If you calculate the step response for the single pole at the origin, you get the straight line. That was model 1. If you calculate the step response for the modified model, that's this one. Ultimately, they become parallel, so the speed becomes the same. But there's sluggishness because of inertia and so forth, so that it takes a while for the real motor to achieve that. So you can see that in the Model 2 response, because the angle does not immediately change when I let go of it. It takes a while for it to start to change. That's inertia. So if I put that model, Model 2, into the feedback loop, then I make a different prediction about the way things should work. That prediction is showed here, right? That's just thinking about system functions, saying that I've got two poles, figuring out where the poles are, figuring out what the time domain response is, integrating it to turn it into a step response, do all those things, and you get a response. The point is that the new model looks like two poles, and when you analyze the root locus, those poles move when you change the feedback. So as I change the feedback number beta, as beta goes from 0 to big, the poles go toward each other and then split off. That's just math. That's the math that was showed over here. All I did was write the second model up there, figure out the system function, find the poles of the system function. They depend on beta. That dependence is shown here. And so the response then, that's where the oscillations come from. If the gain is big enough, I get a pair of poles that are off the real axis. The fact that they have an imaginary component, the poles, means that there's an oscillation. And what happens as I change the feedback is not that the oscillation goes away. In fact, the real part of the envelope doesn't change. That's roughly what I was seeing here. If you watched what was going on in the closed loop configuration, it always oscillated for a couple of seconds, like a second or 2 seconds or 3 seconds. That second or 2 seconds didn't change. What did change was the bumps, how many bumps there were in the 2 seconds, and that's what the theory says. So because the real part of the imaginary pair of poles doesn't change, the envelope doesn't change, but because the imaginary part does change, the oscillation frequency does change. So the result then is something whose envelope doesn't really improve. So that model then, to a large extent, does predict the behavior that I've measured. And then what that motivates is, if I want to make the motor work better, I need some even better controller. Because my simple proportional controller, that's as good as it's going to do. Okay? So what I tried to illustrate today was ways of thinking about feedback to enhance performance. We looked at an op-amp and saw how you could think about feedback increasing the bandwidth or making it faster. We looked at a motor and found out how you could think about changing the motor from being a voltage-controlled velocity to a voltage-controlled position. And we saw how the feedback could be used for both of those. Next time, we'll look at a couple other examples. Thanks.